We're absolutely delighted to have Dame Julia Slingo, Chief Scientist from the Met Office, to come and speak to us. Thank you so much for coming, Julia, especially with all of the natural obstacles put in your path. But you're used to worse random events than this one, I'm sure. That this one will seem like nothing. Indeed, I know one of your big interests is in monsoons, and they're probably even more unpredictable than the British train system. Dame Julia has been at the Met Office since 2009. Before that, she was at the National Centre for Atmospheric Research in the US. She's particularly interested in climate and in tropical weather. She's also been a stout defender of climate change in the kind of public arena, sometimes against rather vigorous opposition from the climate deniers. She is actually the first female professor of meteorology in the UK, and in 2008 she became the first woman president of the Royal Meteorological Society. She's going to talk to us about big data and the Met Office, and we're very much looking forward to your talk, Julia. Thank you.
Thank you very much. It's great to be here, and of course when you arrive at Reading Station and they say that somebody has just been hit by a train in West Ealing, all you feel is great sadness for the families that are going to have to deal with that. So you just say, right, okay, that's not a great problem. I will get here at some point. So here I am. Right, let's put that down there. So it is very nice to be here, and I'll try and whip through this fairly quickly. But there's a lot to say, because the Met Office has been in the business of big data for a very long time. And I think, the establishment of the Turing Institute is a great opportunity for us to see collectively how we might deal with the sorts of big data that we work on. So I hope that at the end of my talk, you'll have a better understanding of what we're all about. I just thought I'd start with some basic facts, just in case you don't know what the Met Office is, other than its presence, albeit limited now, on the BBC. But we are, in fact, the UK's National Met Service, so we have a role internationally as a National Met Service as part of the World Meteorological Organization, part of the UN, and we host the Hadley Centre for Climate Science and Services. So we do both weather forecasting and climate change work. Our annual turnover is about 220 million, and we are a trading fund within BEIS, which means that we are expected to make a return on the contracts that we gain, including contracts from government. And we have approximately 80% of our annual turnover is actually what we call commercial work, where we go and sell our services to the private sector. We're about 2,000 people, of which over 550 sit with me in our science directorate. So we are a major scientific force and have been for many decades the leading atmospheric science and climate science cohort, at least in the UK, and actually in terms of our publication record and our citations and H indices, only beaten by the National Centre for Atmospheric Research in the US. So we have an outstanding academic record in the UK too. We actually have people all over the world. You might be surprised to know that, but all over, wherever there's an RAF base or a military base, you'll find there's a Met Office, and I've been down to see them in the Falklands as one of a really quite big cohort. And we go into fields of war with the military, and we have personnel who are trained military people in uniform. We don't just do the BBC weather forecast, we actually provide services to defence. We're one of two international aviation weather forecasting centres for commercial aviation. We're one and the US is the other. So if you're in an aeroplane anywhere above 20,000 feet, anywhere in the world except over the Americas, that aeroplane is using our weather forecast to tell them how strong the winds are, where the turbulence is, and so forth. We do a lot of international aid, transport, health, energy, marine, agriculture, retail, all sorts of stuff. We provide services to many, many sectors. What are our main drivers? Well, when I wrote our latest science strategy, and somewhere I did bring you a copy, but you can find it on our website. These are the 5 drivers of our science and services. And the first one, of course, is saving lives and livelihoods. And if that's the only thing we do, that we've done our job, really, as a National Met Service. We do much more than that now. We talk about resilience and preparedness, looking further ahead, maybe for the next week, the next month, the next season. How can we get ourselves ready for whatever the weather and climate will throw at us? How do we make wise choices for future adaptation? So the word here is wise. We have spent a lot of money in the coming years on adapting to climate change. It will be very costly, and we need to make sure that money is spent most effectively. And then there's avoiding dangerous climate change. Paris said we should stay below 2 degrees and ideally at 1.5 degrees. How do we go there, and what does that mean, and how will the climate system respond to that, and what are the implications for our carbon budgets and Earth system feedbacks and so forth? I'm not going to talk about those today. But then finally, of course, everything we do is about supporting growth and the green economy. And you might say, well, that's a bit odd, but actually the reason that we sell services to so many sectors is that they know that if they use the intelligence that we hold wisely, they can avoid a lot of costs. So this is not necessarily about making more money, but avoiding costs and actually having a more efficient and effective business. A lot of this is about avoiding costs. So it's often difficult to say what the economic benefits of the Met Office are. But we did have a review a year or so ago, and London Economics did a conservative estimate of a return on the investment of the Met Office of 14-1, which I think in any sector, in any science, if you could get 14-1, you'd be pleased. And that's because avoiding costs, making your businesses more efficient, can produce enormous socioeconomic benefits. And, well, what's behind of that, of course, it's about the business of forecasting. Forewarned is forearmed. We're a sort of fairly unique science in that actually based on fundamental science, we can actually predict with some confidence forward in time. And there are very few sciences where actually prediction is formally based in some fundamental laws of physics in our case. Economics is a very good example, and we've had the Treasury to see us, to sort of see how we do it, and they go, well, you've got a terrific advantage, haven't you? Because you start from Newton's laws of motion, you know. And so we shouldn't underestimate the power of this science and its predictive power as being part of how big data in this case is relevant. I often talk about a lot of interest now in Earth observation, and in fact the Internet of Things and Earth observation. They tell us a huge amount of what's going on today, but they can't tell us an awful lot about what's going to happen next week or next year or next decade, unless they're framed within some predictive framework, and that's really what our science allows us to do. So here we are, and in the Met Office we do forecasting from the next hour to the end of the century using the same fundamental modelling techniques, different, more complex models as we go out longer in time because we have to represent more things like the carbon cycle, like the deep ocean circulation and things like that. But fundamentally it's a unified modelling system. And across those different timescales, stakeholders and customers can use that information in different ways. And that's what's increasingly fascinating about the work that we do. And as you go out, you'll see that actually many of the things that people want to use these forecasts for don't just need information about weather and climate, they need information about other systems. So as you'll see, and I go through the talk, the importance of now mashing data from different sources together, using our predictive power to say something about other aspects of that are societally relevant, like the future health of the population and its exposure to future environments, for example. This enterprise, if you like, is hugely compute intensive, and we were given just a couple of years ago a £97 million investment by the government to upgrade our supercomputing facility. We've always been up there at the very top of some of the most powerful supercomputers in this country, and we've over the years followed Moore's law pretty closely. This time we would normally spend on our 5-yearly upgrade of our system about 30 million. And this time we put together a much more compelling case to say, actually, you know what, if you spent more, the science is ready and waiting, we could do so much more. And we got 97 million. I asked for 125, thought I might get half of it. I got 97 million, so that was pretty good. So this is the new Cray. It's going in 3 phases. The first 2 are in our operational halls now. The third phase is going in a new IT hall on the Exeter Science Park. It will have a less stringent firewall. It's meant for research and collaboration. There is a collaborative building next to it. When it's all installed, 14 petaflops, you probably can't see the numbers here, 14 petaflops, 2 petabytes of memory, 24 petabytes of storage. So we have one of the biggest data stores anywhere in the country. It's a huge beast. Why does it need to be so big? Well, it's partly because when you're making a weather forecast, you are doing a very, very compute and data intensive activity, but you're also doing it in a very limited time window. So people say to me, why do you need such a big machine? I mean, it is a big problem. And the reason the machine has to be so big is that a forecast is no use if it takes you 2 days to make it. So we have to do, and I'm going to describe this in a bit more detail, we have to do all of this in a 2-hour window, and that's why the machine is so big. And in between those operational slots where we make the forecast, we put the research in. So the machine is heavily utilised. It's up there at well above 90% utilisation, and the climate and weather, we're running the same codes on the same platform, swapping in and out the operational requirements. So when you make a weather forecast, you run through a process, and the first thing you do is actually you need to know what the state of the weather is at this moment in time to make a forecast for the next hour or the next day ahead. And we do that. We have to know what the weather is, not just here in the UK. We actually have to know what the weather's doing over the whole globe. Because the weather that we'll experience in 3, 4, 5 days' time could very easily have come from somewhere in the Pacific. And the weather that's in the Pacific would have come from somewhere else, been influenced by something else. So this is a global problem. So we have to simulate the whole globe. So we capture the observations from many, many platforms all over the world in real time through a well-established, internationally agreed free exchange of data from ships, from aeroplanes, from land surface, from balloons, increasingly, of course, from satellites. And each day we process and store about 106 million observations. And even now, we're actually also now beginning to get citizens involved to tell us what the weather's doing. And this is our weather observation website. It was one of the very first, powered by Google, to allow citizens to tell us, to give us data. Some of these people have quite sophisticated weather stations in their back gardens, and some of them are literally just looking out of the window. But we gather hundreds of millions of observations now, not just in the UK, but all over the world, from amateur meteorologists, from citizens. That is going to be increasingly important as our models get finer and finer in scale and the more local information we need. So this is the beginning of the Internet of Things, I think, really, in our domain. We take all those observations from all those different platforms with all the spatial and temporal heterogeneity that exists within them and use a process of data assimilation, where you take those observations and assimilate them into a model, in this case the global model. And that global model, through a very interesting set of mathematics that constrains the observations to obey various physical constraints within the meteorological system, creates a three-dimensional picture of the current state of the atmosphere everywhere in the world. And at the moment, that model has a grid of 17 kilometres, so lots of grid squares all over the world, 70 levels, slices. We're looking at something like 80 million volumes of atmosphere where we have put observations in through a process of data assimilation and minimization of errors, match what the model first guesses, if you like, of what the atmosphere thinks the atmosphere is doing with what the observations think is happening. Then we make a forecast. We run this forward for a week. And from that, we have some boundary conditions for a much finer scale model over here, which we call our UK model, which is running with a grid of 1.5 kilometres. Almost the same number of volumes as this big chap here. This is as computationally expensive to run as that one, because as the grid scale gets smaller, the time step gets a lot smaller. The time step there is about 10 minutes. Here it's 30 seconds or there, something like that. We run this out currently to 2.5 days, shortly to 5 days. And we do that system at the moment 4 times a day. So 4 times a day we bring all these observations in, we assimilate them, we produce the global forecast, we spawn the local forecast, all in a time window of 2 hours. And that will become shorter soon so that we can do an hourly update on the forecast rather than having to wait 6 hours. And some pretty big numbers. And how much, so every day we produce 10 terabytes of data. So this is big data, constantly evolving, constantly having to be analysed. That's the forecasting process. And out of that has done a lot of post-processing and analytics. And we actually produce 4 million forecasts a day that go to many, many customers, many sectors. What you'll see typically is a weather map. There's your iPhone app. And this is the severe weather warning service, which goes to government, to the Cabinet Office. And when we issue a red warning, then COBRA is called and all sorts of things get it going to start happening. So that's what's going on every day. That's the big data that we deal with day in and day out. And of course, it's all about simulation. So when I talk about a model, I don't mean a model that's about empirical relationships or a model that might be a glorified spreadsheet or anything like that. Actually, what we're doing here is simulating from first principles the atmospheric flows and ocean flows, the formation of clouds, the interaction of radiation with the clouds, the atmosphere and the surface. So I don't think I managed to get this to loop. So will it run for me again? I'm not sure. No, I don't think it will. It might if I go back and forwards again, probably. It doesn't want to. I think I've probably overloaded the laptop. what you're seeing here is a rendering of clouds produced by the model, so it looks very like a satellite image, and if it was running again, you would see the sun going past and the clouds building up and then dying down, particularly in the tropics. You'd see the classic sort of weather frontal systems that we would recognise as our weather, and certainly around the southern hemisphere, this continuous sequence of depressions and fronts reaching back into the tropics there. We'd see some tropical cyclones with eyes, all sorts of stuff. It is just a simulation. It's an alternative representation, realisation of the world's weather. This is actually our climate model running at 12 kilometres, so even finer than our global forecast model. And we're coupling this now to an ocean model, which I won't show, but similar sort of structures of ocean currents and flows running at 1/12 of a degree. So an 8-kilometre type ocean model. So you can see the Gulf Stream and you can see all the amazing detail in the ocean. The point is these are simulations, and this is the key point I wanted to make today when we talk about our models. Pity it won't run again, but never mind. I'm not going to spend much time on this because I just want to make the point that actually everything about these models is what we would recognise as classical physics. So it is, if you did physics at A level or physics at university, you'd recognise all these things like the ideal gas equation, mass continuity, Newton's second law of motion, first law of thermodynamics, something called the Clausius-Clapeyron equation, the Planck and Stefan Boltzmann's law that tell us about infrared radiation and the greenhouse effect, and Kirchhoff's law. Those fundamental laws, when I started off in climate modelling in the 70s, building the first climate models, actually give us 75% of the answer. And that's really important because these models are really, really constrained in their simulation by these immutable laws of physics. And what we do, of course, is solve them by cutting up the Earth into this grid that I've already talked about and slicing the atmosphere and the ocean and the land surface up into layers. And we integrate these equations, and there's some quite complex mathematics on how you discretize these equations on a grid. That in itself is a very interesting problem, not still to be solved really, ideally, but how you solve these equations numerically on a grid in a way that's computationally efficient, where you conserve the variables that you're integrating forward in time. All those things are actually a very big mathematical problem. But perhaps the biggest problem that we faced in this field is that a lot of the physics that's fundamental to our weather and climate goes on at scales smaller than the model grid. So at 17 kilometres, here's a lovely satellite. Well, actually, I think it, I'm not sure whether it is a satellite picture or whether this came from a spacecraft of a huge thundercloud, probably over the tropics somewhere. And we can see the complexity of this cloud system with lots of small clouds, some slightly bigger ones, this enormous thunderhead and so forth. Lots of things going on at a myriad of scales. So what we have here to deal with is that we're trying to do the simulation at a particular resolution when we know that the system is multi-scale and the energy cascades from the small scales to the large scales. And how do we handle this sort of physics that's going on? Here's, say, a model grid box, but it's all this stuff going on at much finer scales. Now, of course, we have the computational power to simulate at enormously fine scales and understand all these multi-scale interactions that take us up to the resolved scale of the model grid. But fundamentally, we have to what we call parameterize all of that within some simple set of equations. And this is where the empiricism comes into models. As the resolution decreases and we get more granularity, then some of these problems start to be resolved, and we've made some fantastic progress over the last few years with these kilometre scale models and sub-kilometre scale models. But as you go down in resolution, you find, of course, that there's yet another set of problems to deal with, and this one is just highlighting the very complex chemical process, cloud processing, that goes on in a cloud, so the cloud microphysics. And if you're interested in climate sensitivity and how clouds will respond to climate change and to pollution and things like that, then you need to understand these things. So even though we have more compute power and the models get more realistic and we can resolve more things, you're still pushing down more and more into the finer scales where there's still a to do. And one of the ways we try and understand that is actually to have things like our research aircraft that we share with NERT, where we go around and fly around in clouds to look at these sorts of processes, so we can actually try and represent them more exactly in our models. So this is what I've spent my career on, is trying to deal with the physics that goes on at the scale smaller than the resolved grid of the model. And this is still where, when we talk about uncertainty in models, this is where the uncertainty is, that final 25% that we don't get from these fundamental laws, which is difficult. The other thing, of course, that's interesting about the forecasting process is the whole business of chaos theory. And this was one of the other things I wanted to really talk to you about today. This is Ed Lorenz. He probably should have had a Nobel Prize for what he did, but he was a very self-effacing, very, very humble man. But his influence, not just on meteorology, but on many fields of science, has been quite profound. And he wrote in '63, "One flap of a seagull's wings may forever change the future course of the weather." So this is this concept of chaos, that tiny perturbations can grow through a physical system and affect the large scale. It's not the same as randomness, and it's really important when we talk about chaos. Chaos, the evolution of a chaotic system, knows where it's come from, whereas a random system doesn't know. If you toss a dice, it makes no difference what you tossed the time before. But in a chaotic system, the chaotic system will know where you've come from, because it's a physical system. And he basically solved this set of nonlinear equations, very simple but actually very profound, and showed that with tiny, tiny perturbations to the initial conditions, this system would replicate itself for a while, and then it would start to go off, and you would get different solutions and different regime behaviour as time went by. And now this has become deeply embedded in how we do weather forecasting, because he was absolutely right. One flap of a seagull's wings may forever change the course of the weather. And we get, this is the Lorenz attractor, but you could think of this as two possible sort of states of the weather, settled or unsettled weather. And whether you spend more time in one part of the attractor than in the other depends on all sorts of things to do with the system itself, but actually where you started from. And one of the other very profound things he said is that the predictability in a system is flow dependent and predictable. So whilst we will say sometimes that in weather forecasting the limit of predictability is about a week, there are occasions where it's about a day, and there are other occasions where it's about 2 weeks. And that just depends whereabouts you start, what sort of state your atmosphere is in when you start your forecast, and how an initial perturbation will grow or not grow. And this is just an example from the Lorenz model here of a system here which is starting up in this state. You might say this is a fairly unsettled pattern, but it's a point in the attractor where the system's not going to diverge very much with a small perturbation, and it's actually heading off into the other type of the weather regime in a very predictable way. In another situation, it's coming down and it's getting caught here between these two lobes of the attractor, and you'll probably get two quite distinct solutions, and I'll show you an example in a little while. And there's another where the initial state that you start with is in itself pretty unstable, and small perturbations can take you anywhere. And we see these in weather forecasts where the forecaster says, I'm honestly not quite sure what to say. These are all fundamental characteristics of a chaotic system. But we are now in a situation where we do know that these are predictable. So when we make a forecast now, we never make a single forecast. We actually make 40, 50 forecasts. And even with our very fine scale, kilometre scale model now, we do make, every time we run the forecast out for a day or a day and a half, so we make 12. Because even though you go down in scale, the flap of the seagull's wings still matters. It's a different process that's coming into play. That upscale cascade of energy still goes on. So how we do it is that we know there's an uncertainty in the initial condition. We don't know in fine detail what the current state of the atmosphere is. So you put some perturbations on that, and we design those in a very formal way to maximise the growth rate. So we know where in the system are the optimal places to put perturbations. And then the forecast will evolve, and you will end up with a set or a phase space here of solutions from the forecast, which, if the model is good and reliable, will lie within the current climatology. In other words, it's representative of the weather that we know happens in, say, in this country. That doesn't always the case, so some models will have biases and they fall outside that. But a good, reliable model will be able to replicate the statistics over a long period of what we think the current climate is. Going back to what I was saying about clouds and things, of course, we know that these physics that's going on at scales smaller than the resolved grid of the model are also stochastic. So we now also introduce formal ways of representing that stochasticity in the formulation of our parameterizations. So there's another element that comes in called model uncertainty. And those two combined now give us, and we can estimate this formally, an ensemble prediction system that is as dispersive as it should be. And we found that without the model uncertainty, the forecast system was under-dispersive and therefore overconfident. So this in itself, there's lots of literature on this, and Tim Palmer and I wrote a generic paper on this problem, this issue, that's in the Philtrans, if you want to read it and learn a bit more about all this. But this underpins everything, and I'll talk a bit more about that going on now. So I was going to use now Storm Desmond, which happened last December, and this is Carlisle. It was quite an extraordinary event, just to show you what I mean about how we do forecasting and how we then went on to estimate flood risks. So this is Storm Desmond. Unprecedented, at least in 100 years of rainfall records. Huge amounts of water came out of the sky. Quite extraordinary. And it was associated with, sorry, I need to go back. A weather pattern, I'm sorry this is a bit small, I meant to blow it up for you a bit. The UK's in here, and what we had was a very strong southwesterly flow coming up across the southern half of the country with a lot of embedded fronts, and there's a little low here. These are ripples that developed on this southwesterly flow. And we would recognise this as something we call an atmospheric river. This was carrying huge amounts of moisture. It was very warm. It had come right down from the deep tropics, very unstable, lots of fronts, and it was pointing directly at the Lake District. I call it the hose pipe, pointing directly at the Lake District. To the north was a very deep depression, and one of the key difficulties, as we'll see, is that depending on this air that's coming around the southern flank of this low here, has come all the way from the Arctic. So you have an air mass here that is cold and dry, and an air mass here that is incredibly warm and wet. And we were having to try and say, well, where's the dividing line? And how confident are we with that? This was our global forecast system 5 to 6 days before the event. And so this is what the forecaster has. He has a whole load of forecasts to look at here, and this is just a snapshot of them. And what you see, of course, is, from the forecaster's point of view, sort of a bit of a warning here. I've got a low to the north on virtually all of these forecasts. And I've got quite a lot that have some southwesterly flow, so I might be a bit anxious about this. This looks like a very unsettled spell of weather. But his dilemma, of course, is that he has one member that looks exactly like what actually happened, very strong southwesterly flow. Here's a little low forming on that front between the warm, moist air and the cold air here. Cold air's coming round, clipping Scotland, but the bulk of the UK is in the southwesterly. And he's got another forecast like that, where the trough has developed much more and all the cold air is coming across the country. So he has to make a decision. What's the probability? But also, what's the impact? So even if only 10% of the forecast look like this, you're going to put up probably a yellow or amber warning. And we did that 5 days before Boxing Day. Same sort of thing. 10% chance of heavy rainfall in south of the Lake District. And we ought to watch this. It's only 10%. If it happens, the impacts will be huge. Now, when you get a bit further in, you start to see that the forecasts are now all converging, just as you would expect from Lorenz's chaos theory. Closer to the event, the more they're converging. This is rainfall, and the white areas here are heavy rain, and you can see the hose pipe now. It's pointing straight at the UK. But where in the UK? We have one forecast here that's putting all the heavy rain over the Lake District, but not terribly heavy. We have another forecast here that's putting some really intense rainfall right up into northern Scotland. So even 2 to 3 days out, this is tricky. What we now do, of course, is to actually go away and say, well, actually, this is the global model. It doesn't see the mountains very well because the resolution's too coarse. What does our fine scale model do? So the importance now of scale becomes absolutely paramount when you're in situations to do with rainfall and flooding. This model of the Lake District is at a 12-kilometre grid. Remember, our global model is at 17 kilometres. Not so long ago, this would have been the best that we could do, even at a regional level. The Lake District looks like that at 12 kilometres, so just a little bump. And the rainfall, this is the Cockermouth flood event, actually, in 2009. The rainfall for that Cockermouth flood would have looked like that in that model. This is what we currently run. That's what the Lake District looks like in our kilometre scale model. And that's the rainfall that came out for Cockermouth floods. It's a very, very good forecast. And we were able to save a lot of lives and livelihoods because of that. If you're a walker, you'd recognise the Lake District in that one, but you wouldn't in that one. So when we got to Storm Desmond, this was the forecast that we were then beginning to get of hourly rain rates coming out of a kilometre scale model. This looks very like a radar image. And we can see that over time it's locking on to the Lake District and the rain rates are approaching 16 millimetres per hour or more for hours on end, which was why we went red. And we were right to do so. So that's the way in which now we can use simulation to go from the global to get the probabilities of the synoptic, the large-scale weather, and then use these finer scale models to get down to the local detail and the impact and the hazard and so forth. But what about the longer scale? So the other thing that actually Ed Lorenz also talked about was what happens when you have a chaotic system that's forced. And he looked at the influence of an external forcing factor, F. If you add that to that system of nonlinear equations, how does that change the shape of the Lorentz attractor? And in weak forcing, what you find is that the number and spatial patterns of the sorts of regimes that you see remain the same, but their frequency of occurrences change. So when I worked on the Indian monsoon and looked at active and break cycles of the monsoon, I knew that El Niño tended to populate the break more than the active phase, but they looked the same. When they were there, the meteorological flow patterns and everything were the same. It's just that one regime was more prevalent, likely to be more prevalent than another. That's what that's saying. But in strong forcing, the number and patterns of regimes may be modified. And as the atmospheric system goes, and the atmospheric system may go through bifurcation points. This is what we worry about for climate change, that when you warm the planet so much, the forcing is actually very large. We may go into climate regimes that we have not observed before, and it may be very difficult to get back to the past climate. What we call, the collapse of the thermohaline circulation might be regarded as a bifurcation point. So his ideas are really important for how we think about future climate and climate change, because what he's actually saying here is that, in other words, unlike weather forecasting, it's not possible to say what the weather will be like at any particular place on any particular day. It should be possible to say what the statistics of the weather might be over the coming season or decades, if we believe that this chaotic system responds to forcing in these sorts of ways and we understand them. So this is at the root of understanding climate prediction. And a lot of people misunderstand that. They say, well, if you can't forecast the weather more than a week ahead, why can you talk about climate prediction? We're not talking about the same thing, essentially. We're talking about what's captured here. So a good example, actually, is our seasonal forecasting. And we do that now operationally. And this is looking, in this case, at something we call the North Atlantic Oscillation, which drives our winter weather. So this is a regime, a pattern of weather, where we tend to get mild and wet winters. Not every day, but the prevalence is for mild and wet. Last winter was a good example. But there are many reasons, many forcings, that F, that drive that. It can be the 11-year solar cycle. It can be the changing Arctic, volcanoes do, the winds in the upper atmosphere, El Niño, a pattern of tropical weather, and the state of the North Atlantic Ocean. These are all things that we've explored scientifically over the last decade and understand how they shift the weather to be in different lobes of the attractor, if you like. And so on the basis of that, we were actually able to say that the risks of spells of windy or even stormy weather is expected to be greater than usual for the time of year. This was our forecast last autumn. And it was spot on, and actually it was driven a lot by El Niño. This year we're actually suggesting that it might be colder and more easterly in December, so see whether we've got it right. The point is that you can never be right or wrong. It's a probabilistic forecast. And it's about understanding all of that is understanding that your model is reliable. And then you have to decide how you handle the probabilities and how would the government use that information. It's really important. There's another way in which we can use some of this stuff, and this is just, I think, the final point. After the Storm Desmond, the government set up the National Flood Resilience Review, and Oliver Letwin said to us, well, he said, dear Met Office, never again in my lifetime do I want to see this. And you need to tell me how bad the rainfall can be. And you go, well, how long's a piece of string? That's a really, really difficult question. And it was indeed, pretty challenging, because the way that flood risk has been estimated up till now in this country is to take the observed record of river gauges, flow rates, and apply extreme value theory to them to get the tails of the distribution. But you're lucky if you've got 30 or 40 years of data. And yet, we know from history that these things have happened before. So we thought, well, we'd have to come at this in a slightly different way. And so here we are again, one flap of the seagull's wings, and Ed Lorentz. And you can say, well, actually, although we use this as the basis of forecasting and looking at forecast probabilities, you can also apply it to the real world. That the evolution of the world's weather that we've observed in the last 100 years is only one possible path that the world's weather could have taken. Because we've done things, we've made decisions to chop down trees or whatever, we've been the flap of the seagull's wings. So there are many, many, many plausible paths that the world's weather could have taken, and observations are just one plausible realization. So I asked the question, can we use a climate model simulation now to find plausible alternatives that have experienced the same forcing, that are perfectly plausible meteorologically, but could give us even more extreme rainfall than the UK has observed in its instrumental record? It's a really interesting question. So that's what we set about doing. We called them black swans. And we're looking for them in a climate model event set. So this is coming back to the point that the model is a simulation with all the degrees of freedom of the real world to do whatever it wants to do within the confines of the greenhouse gas loading in the atmosphere, what the sun's doing, and what some of the deep ocean circulations are up to. But other than that, it's free to do whatever it wants. Provided, of course, that it's reliable. So it has a plausible simulation of those weather patterns that we know bring heavy rain to the UK. We've only just got models where I could say that that's true, and it's only just acceptable. But this is the future, from my perspective. As I said, simulations must sample the same forcings, the same F, as the real world, but must have sufficient freedom to evolve to different regional climate and weather regimes. So what we've done is to take, and this was stuff we had off the shelf, when we set up our decadal forecasting system for climate, we actually do lots and lots of simulations over the past 35 years, in this case, to look at the reliability of the system. So we ended up having 1,400 years of simulation for a 35-year period. So effectively, what you've got is 40 times more samples, 40 times more plausible pathways of the world's weather than we've observed. And so you can start to say, well, what does the PDF look like? So this is monthly mean rainfall here for each month through the hydrological winter. The black is the distribution of the observations, which immediately show you how poorly sampled the extremes are. And these are all the model realizations, and what we've done here is just colour the ones that are more extreme than any of the existing records. And this is for South East England. So what you've got here now is something that tells you actually it's meteorologically and physically plausible that you could see much more rain than we've currently observed. It also says it can only be, there are bounds to this. This is still not that big a sample, but it's giving us quite a sense of what's out there. And so what you can then do is to take all those, and we took them for different parts of the country and estimated a range, which is the grey swath, and we said, what's the chance of an event which would break the existing record, be 20% higher than the existing record, or 30 or so forth. And what you get there is a sense of that in any year in one of these fairly large regions of the UK, there's a 10% chance of a new rainfall record. So we shouldn't be surprised when we get dumped on. We could go out with 1,400 years of simulation and be fairly robust at a 1% level, or what the Environment Agency might call a 1 in 100 year event, which is, again, communication. We didn't believe that we had anything like enough samples to talk about a 0.1%, which is the 1 in 1,000 year, which is often what's used for resilience. And you have to say, where does that come from when you've got 30 or 40 years of observations? But we felt from this that we could say that there was between 20 and 40%. There was a 1% chance of that we could see 20 to 40% more rainfall just from natural variability than we've already seen. Really exciting stuff, because if you can do this for rainfall, you can do it for heat waves, you can do it for drought, you can do it for air quality, you can do it for all sorts of things that affect people. I'm going to nip through this. We then went on to use that information to stress test the extreme flood outline. And this is Carlisle, this is the floods in Carlisle. And when we dumped even more rainfall on Carlisle, 20% more rainfall, actually you stayed within the extreme flood outline. There was a bit more flooding. The extent is actually determined in this case by the landscape. The flow of water through Carlisle and the damage to embankments and bridges would have been quite significant. And then you can combine that information with all sorts of information about critical infrastructure, phone networks, electricity supplies, water supplies, Wi-Fi, all those things that affect people even if they're not flooded. And that's a really key point. And that basically brought us to a major recommendation in the flood review, is that we need to be joining models and joining data. And this is where really we get to the Turing Institute at last. Because if you follow what actually is probably now the right way to look at environmental risk, from starting from global weather to local weather, to the, in this case, hydrology and inundation and impact and response, and then you can even say, well, if I poured concrete here, I could do the what-if experiment in my simulation pathway and say, what's the residual risk of having taken that action to mitigate flood risk? Do I plant trees all over the hills? The simulation process will allow you to say, actually, it makes damn all difference. Or it makes a difference, but here's the residual risk. So this is really powerful, but it requires us to have both what I call a modelling stack and a data stack. So you need to have the exposure vulnerability data in here, along with our meteorology and hydrology, and then you've got to communicate it in a way that makes sense to people. And all of this, we would argue, needs to be set within a formal probabilistic framework with propagation of uncertainty down the value chain, which we don't currently have, because we do it in a very sophisticated, scientifically formal way at that end, and it's virtually non-existent down this end, and that needs to be sorted out. And then how do you communicate probabilities in a way that allows people to take action? So very finally, one of the things that I think is of real interest with what you're doing is that we're thinking a lot about how do we deal with what we call the rat's nest. That over the years, as we develop larger and larger data volumes, more and more services, you end up with a system where there are so many dependencies on data and data formats and so forth that it becomes a complete rat's nest. And we've gone now to a process where we're decoupling our data, our basic data, from a lot of the downstream systems. So this idea of a core data interface or decoupler is really important part, I think, of future data structures when we think of having to deal with big data, particularly big data that's changing all the time. So here are our model data. They're changing every day, but also actually we upgrade the model. New science comes along. Does the customer need to have to change all their processes to deal with that? No, they shouldn't do. We should be able to decouple what we're doing in the R&D path with what needs to go on down this end. So this decoupler is really important, and how we do that, it's about data formats, it's about good metadata, it's about regridding data and conserving its fundamental properties, all those things. This is really integral to the future of certainly what we do. And then we can bring in, including third-party data here through that process to provide products and services. And this is, I think some of the interests we have with you, really important. We've set up an informatics lab at the Met Office between my team, science, and the head of technology, Charlie Ewan, who I think you may have met. And there's lots of exciting things here on how we've experienced the weather, fly through it and all of that. Some really innovative ways of taking terabytes of data and getting in there fast and finding the bit that you want to know about. How we deliver it on things like apps. This is Alexa here. We have an Alexa. People know what Alexa is. There was a piece in the Times yesterday, I think, about Alexa. We have one of the first Alexas, and we talk to it and ask it questions about the weather and when should I go for a run, and it comes back instantaneously and tells you when would be a good time to go running in wherever you live, and things like that. So we're doing some really innovative things of how do you do useful and scalable things fast with data. And it's been a really interesting experiment. I'm sure there's something similar going on here where we've brought 8 very creative people from technology, design and science, and they sit in a collaborative space, very much like you have here. The design chap is really important. He's right at the beginning of the process, because that's what people are going to see at the end of the process. So I think this is really exciting, something that we'd like to, I think, explore more with you. And finally, very grand statement, but big data and 21st century challenges. When I talk about weather and climate, I have to talk about it not just in terms of the bit that I know about, but in the context of urbanisation, population growth and limited natural resources. Those are what are going to determine our socio-economic future in this planet. Those things together, and around those are the securities on which we rely for our health and well-being. And none of them are independent. And I get pretty upset when people talk about food security but don't talk about water security, or talk about food security and not energy or health. We have to look at this as a complete problem, because otherwise it's not going to make sense and we're not going to find the solutions that we need to find. So the key points that I think I wanted to make today is, as you develop your thinking, synthetic data from simulation is going to play an ever and bigger role through the 21st century. That's what we do. Synthetic data alternative worlds really, really important. I think we've got to think how we deal with uncertainty for risk-based solutions. It's not at all clear how you deal with uncertainty. And how do we communicate actionable information? How do we condense all the data we have into a single message on an iPhone, for example? And I think we need to find much better ways, methodologies for linking models and linking data. And decoupler was a start. And actually, how do you integrate models and exchange information across them? So I'm sorry I was late, and I'm sorry it's got even later, but happy to take some questions.
Well, that was a fascinating talk on an incredibly important topic, and helping the world to manage the risks that are related to weather, whether it's on a kind of personal level or on the kind of larger scale, is very important. And as you say, I think very interesting to us because we are kind of consumers of uncertain information. And I think, I see the Alan Turing Institute as a little bit representative of perhaps other customers at the consuming end of the information that you're producing. We have a little bit of time for questions, but I wanted to begin with one, which is, I suppose it's probably fair to say that you can't possibly take responsibility for or know the loss functions of all of your information consumers. So, we're thinking about how you make decisions based on the weather. In many cases, you can't make decisions because you don't know what the loss functions are in the heads or in the systems of your. So, are you expecting, as the Met Office, to provide a sort of premium service, which is the full probability distribution? Someone talking to their Alexa may be happy with a single answer, but really, what you've told us today is that the full answer is that distribution. Are you thinking in terms of providing that distribution to people, to sophisticated users that can make their own decisions?
No, not really. We have to do it in partnership. And so, I mean, if I go back to this one. We already do, when we do flood forecasting, which is essentially this whole stream here, we do it in partnership with the Environment Agency, and they would do it in partnership with their local government people and so forth. We have something called the Natural Hazard Partnership, where we link with the Environment Agency, Public Health England, Scottish SEPA up in Scotland, the devolved administrations. And it's very clear that for us, we do this bit of the food chain. We start here, and we probably will go, we have some role in this bit down here. But after that, we must partner, and that's really important for us. So
well, there are only 2,000 of you, so...
No, and this is what we're good at.
Yes.
And I think the whole point for us of going through this process of thinking about the rat's nest is thinking about how do third parties, in a sense, come in at this point rather than having to know all the gory details of all this stuff that we do. How do they come in at this point to deliver a product? And we may not actually be involved in the end in the delivery of that product. That's perfectly possible. Often we are, because they're often 24/7 operational products. So there's some involvement. Like we have the Flood Forecasting Centre is run in partnership with the EA, and they sit as a team in the Met Office because they need that 24/7 capability. And a lot of what we do now, so if we look at the Severe Weather Warning Service, when we colour it red, it's both a probability of the hazard happening, which is this bit, combined with the size of the impact, which could be the Environment Agency, or it could be Highways England, or it could be National Rail Networks, or whoever it is, who understand their loss function. And it's understanding that matrix between likelihood and impact that helps you determine then what
How about the sort of the private company, so maybe an insurance company that you've never met?
So we do masses of work with the insurance company, and in fact, I mean, going back to this figure here, I mean, they are incredibly good at this impact end. They have the vulnerability exposure data. They're quite good at the hazard, but actually they've recognised that actually they need to partner with people like us and the hydrologists or whoever to get at the hazard better. But we will never do this. No. It's not our bag. But we have to be sure that our data can be used by other people as effectively as possible.
I wonder if others have questions. Yes, over here.
Just in terms of climate change and with all that you know, like, is it something that keeps you up at night, or? Just in terms of, hello?
It's working.
Just in terms of climate change and all that you know about it, is it something that keeps you up at night, or are you quite happy with government policies and where we're going right now, like in tackling with it and trying to reach that 2% target?
I'll have to give you an unofficial answer, because actually, as the Met Office Chief Scientist, I stick only to what the science says, and I don't advocate anything. But let's be clear, the science is very clear on this, that if we don't do something pretty fast and reduce our carbon emissions, we are heading for a world that will be extremely challenging. And the targets that were set in Paris will require a scale of response that we have not yet seen from governments. And whether it's doable, I don't know. If we head towards a world where we are 3 or 4 degrees warmer than pre-industrial, we will have some very serious things to deal with that are sort of represented in that circle of securities that I showed at the end. Do I stay awake at night a lot? Sometimes, when people try and discredit the models and the science, and to sort of say it'll all be fine, of course, because I'm all right. Do I think that we'll find a way through it, through clever technology and engineering and so forth? Yes, I hope so. But will it be in time to avoid some pretty serious impacts? Probably not. So if you live in Bangladesh or any of the low-lying island states, it's already too late for some of these people. And we need to recognise that.
Any other questions? One over there.
Hi. So I think you hinted at a move towards sort of crowdsourced measurements. What sort of checks and balances do you think you will have to put in place to ensure that it doesn't add to the initial condition uncertainties?
Yes, now that's a really, really good point. So I don't think that crowdsourcing data will ever replace what we would consider our conventional observing system of very high quality, highly calibrated instruments like our radar network or satellite data or balloons. But they can be used in conjunction to add more information. They're poorer quality, they're not as well calibrated, they have a lot of issues. But if we can use them in combination, they of course give us a lot more detail. And sometimes we can use them not necessarily directly into the model, but we can use them on the forecasting bench so that the forecaster can modify the advice to the customer. So they come in at different points in the forecasting process. So for us, a really good example is the forecaster's nightmare is in winter when we have, is it snow or is it rain? And actually, the citizen coming in and saying, it's already snowing. is really useful information that we can use to then modify the real-time forecast. So there's a mixture of things. But the key point for me is that you must have a high-quality set of observations against which you can calibrate the rest of the stuff. And if we lose that and just think that more data is all good data, we'll be making a really bad mistake.
Time for one last question. Yes.
What is the limiting factor in improving the quality of your forecasts? Is it the amount of computation power you have available to you? Is it the accuracy of the model? Is it the amount of data that you have available to you today, observations, or something else, or is it a combination of all of them? If you could improve one of them, which one would you most want?
Computing power. Always. We've been waiting for years to have the compute power to run the models at these sorts of resolutions that I've talked about. And we've known for years that if we could do that, they would improve dramatically. In the same way that if your model is better, your data assimilation process is better, and therefore you can utilise all the Earth observation data more effectively. So we've argued for years, actually, that the amount of money that's spent on Earth observation and satellites, which is huge compared with compute power, is unbalanced, because we throw virtually all that information away. We can't use it because the models are not granular enough, either vertically or horizontally, to take in that information. So for us, it's compute power, compute power, compute power. And the improvements in skill over the last 4 decades in forecast skill nearly always come from model improvements, which of themselves then allow you to utilise the satellite information more effectively.
Very good. Well, there are so many more things we could ask you, Julia. It's been a fascinating talk.
Sorry I was so late. Yes.
Can't be helped, but it was absolutely worth it. And as we go out, I think there's more tea. Yes? Yes, there's more tea if you can stay for more tea and chat. And you've had a lot already, of course, but I encourage you to stay for more if you can. I'm certainly going to talk to Julia, and please come and join me. You're asked to give your badges back on the way out, and the exit is the same one you came in, back into the main library when you do eventually go. Thanks so much for coming, and Julia, thanks for a fascinating talk.